Welcome back, everyone. Today, we're going really small. Like, incredibly small.
We're talking atoms, right?
You got it. We're diving deep into atomic structure to understand, the nuts and bolts of electricity.
It's amazing to think that something so tiny can be responsible for something as powerful as lightning.
That's exactly what we're going to unpack today. We've got some great resources like diagrams and explanations, even some practice questions to make sure we're getting it all.
It's fascinating stuff. We'll start with the atom structure, then move on to electrical charges and static electricity, and then, we'll tackle the big one, lightning.
So if you've ever wondered why you get a static shock or how lightning forms, well, this is the deep dive for you.
It all starts with the atom. To really understand electricity, you've got to understand the atom first,
Our sources do a great job of breaking down the key areas we need to cover.
right? Like, what is an atom made of? What are those charges everyone's talking about? And how does it all connect to, the static shocks and lightning?
So let's jump right in. Atomic Theory 101. What is an atom?
An atom is like the tiniest building block of everything, right?
Yeah.
And inside each one, you've got these three subatomic particles: protons, neutrons, and electrons.
Not just floating around, though, right? They have a specific arrangement.
Exactly. The protons and neutrons, they hang out together in the center of the atom, which we call the nucleus.
Like a tiny little sun in our solar system.
And then you have the electrons zipping around the nucleus, kind of like planets orbiting the sun.
Figure 1-1 in our material shows this beautifully. It's a really helpful visual.
Yeah, definitely. Now let's zoom in and take a closer look at each of those particles, starting with protons.
All right, protons. What makes them special?
Well, they have a positive electrical charge. And as figure 1-2 shows, they have these lines of force going straight out in all directions.
Lines of force. Sounds kind of mysterious.
Imagine like an invisible force field around the proton. That's how it interacts with other charged particles.
Okay, so protons, positive charge, lines of force radiating outwards. Got it. What about neutrons?
Neutrons. Now, these guys are the neutral ones, no charge at all. And because of that, no lines of force either. Figure 1-3 illustrates that pretty clearly.
So they just hang out in the nucleus, chillin'.
Pretty much. But they do play a critical role in keeping the nucleus stable. More on that later, maybe.
Sounds good. Now, on to the last of the trio. Electrons.
Electrons are the tiny speedsters of the atom, much smaller than protons and neutrons.
Our source says they're only about 1100th of the mass.
Yeah, incredibly light. And that's important because it's what allows them to easily move around and participate in, in energy transfer, which is basically what electricity is all about.
And of course, electrons have a negative charge, right?
Right, the opposite of protons. And their lines of force, instead of going outwards, they go inwards towards the electron. Figure 1-4 shows that.
So we've got the protons and neutrons in the nucleus and electrons whizzing around them, and each of these particles has a charge, and those charges interact in specific ways.
Exactly. Like charges, they push each other away. So two protons would repel each other, and two electrons would do the same.
And opposite charges.
Opposite charges attract. So a proton and an electron, they want to come together.
Like the classic saying, opposites attract.
Exactly. And these attractions and repulsions, they create what we call an electrostatic field. It's basically the area around a charged particle where its influence can be felt.
Okay, so any charged particle has this invisible field around it where it can either attract or repel other charged particles.
And there's a law that describes this whole interaction, Coulomb's law. In a nutshell, it just formalizes what we just talked about, like charges repel and unlike charges attract.
So it's all about that balance of charges.
Precisely. And that balance, or sometimes imbalance, within an atom is what determines its overall atomic charge.
So an atom can be positively charged, negatively charged, or neutral, right?
Yep. A neutral atom, like the one shown in figure 1-9, has an equal number of protons and electrons. Their charges cancel each other out perfectly.
It's balanced.
Exactly. But if an atom gains extra electrons, it becomes negatively charged, like in figure 1-10.
And if it loses electrons, it becomes positively charged, right?
Precisely. Figure 111 shows that. These charged atoms, we call them ions, and they play a big part in a lot of chemical and electrical processes.
Okay, I think I'm getting this charge thing now. And this all leads us to static electricity, right?
Absolutely. Static electricity is basically what happens when you get a buildup of either negative or positive charge on a surface.
So like when you rub a balloon on your hair and it sticks to the wall.
Exactly. What's happening there is that the rubbing is transferring electrons from one surface to the other.
So one surface becomes negatively charged and the other positively charged.
And then, because opposites attract, They stick together.
Now, what about those little shocks you get sometimes?
That's electrostatic discharge. So what happens when that built-up static charge suddenly finds a path to flow to another object?
Like when you touch a doorknob after walking across a carpet.
Yeah. The friction from the carpet can build up a static charge on your body. And when you touch the doorknob, zap, the charge jumps from you to the doorknob.
Figure 112 shows this really well.
And sometimes those discharges aren't just a little zap. They can actually be dangerous, especially around flammable materials.
Our source mentions this in Figure 114.
Yeah. If there's enough static buildup, that spark can be enough to ignite flammable liquids or gases. So it's important to be aware of that in certain environments.
So that's static electricity in a nutshell. Now, ready for the big leagues?
You mean lightning?
You bet. Lightning is basically a massive electrostatic discharge. But instead of between your finger and a doorknob, it's happening in the sky.
Way, way up in the sky.
Yeah.
And it's a lot more powerful, obviously.
Figure 115 gives us a really impressive view of different types of lightning.
And it all starts with charge separation in clouds, usually storm clouds.
The text explains that this happens because of friction from air currents moving within the cloud.
Right. Imagine those tiny water droplets and ice crystals colliding and rubbing against each other.
Creating friction.
Exactly. And this can cause different areas of the cloud to become either positively or negatively charged.
Typically, the bottom of the cloud becomes negatively charged.
And that negative charge can induce a positive charge on the ground below.
It's like they're reaching out to each other.
And that's when things get really interesting. This intense negative charge at the bottom of the cloud starts to create an ionized path towards the ground. It's called a step-down leader.
Figure 116 shows this step-down leader. It's like a staircase of ionized air reaching down from the cloud.
And at the same time, from the ground below, a positively charged path starts reaching upwards. We call it a stepped-up streamer.
Like they're trying to connect, almost like a handshake.
That's a great analogy. And you can see this stepped-up streamer in Figure 117.
And then bam, the moment those two paths connect, that's the lightning strike.
That's when the negative charge from the cloud rushes down to neutralize the positive charge on the ground.
Creating that incredibly bright flash of light we all know. And Figure 118 captures that moment of connection perfectly.
And all that energy being released so quickly, that's what creates the thunder. The air heats up so rapidly that it expands explosively, creating that sonic boom.
Wow. It's amazing to think about all that happening in a split second.
And of course, lightning is incredibly dangerous. Figure 119 is a stark reminder of that. Every year, lightning causes deaths, injuries, and tons of property damage.
The text explains that when lightning hits a non-conductive object, it creates a ton of heat at the point of impact.
Enough heat to crack concrete or even start fires. It's serious stuff.
Fortunately, we've developed ways to protect ourselves from lightning strikes, right?
Yeah. Lightning protection systems. Basically, they provide a safe path for the lightning to travel to the ground, bypassing structures and people.
Like a detour for lightning.
You could say that. The most common type of lightning protection system uses an air terminal, also known as a lightning rod. You've probably seen them on top of tall buildings.
It's that pointy metal rod that sticks up.
That's it. It's designed to attract the lightning strike and then channel it safely down to the ground through thick wires.
Figure 120 shows a typical lightning protection system. It's really ingenious how it intercepts the lightning and diverts it away from the building.
It is. So yeah, we've covered a lot of ground today,
Yeah.
from the smallest particles to some of the most powerful natural phenomena.
It's amazing how it all connects back to the atom. To wrap things up, let's test our knowledge with those practice questions from part 1.1.pdf.
Sounds good. Ready to see how much we've absorbed?
I think so. Question 1. Atoms contain 3 types of subatomic particles: electrons, protons, and neutrons. The electrons orbit around the nucleus of an atom.
Yep, that's definitely correct. Electrons are those tiny particles zipping around the central nucleus.
Okay, question 2. B. Protons do not participate in the flow of energy, and they have a positive electrical charge with lines of force going straight out in all directions.
Right again. Protons are in the nucleus. They have a positive charge and those outward lines of force, but they don't flow like electrons do.
Question 3. C. Neutrons have no charge and therefore have no lines of force.
Correct. Neutrons are neutral, so no electrical force is involved.
Question 4. Because of their light weight, A. Electrons actively participate in the transfer of energy and have lines of force going inward in all directions.
That's it. Their lightweight makes them super mobile, and they have those inward lines of force.
Question 5. The D nucleus of an atom only contains protons and neutrons.
Absolutely. The nucleus is the home of the protons and neutrons.
Question 6. Coulomb's law states that particles with D-like charges repel each other.
Correct. It's one of the fundamental rules of electricity. Like charges repel.
Question 7. Coulomb's law states that particles with C, unlike charges, attract each other.
The other half of Coulomb's law. Opposite charges attract.
Question 8. The atomic electrostatic D charge of an atom is either balanced, negative, or positive, depending on the number of electrons compared to the number of protons.
Right. It all comes down to that balance of charges.
Question 9. If an atom contains an equal number of electrons and protons, the atom has a balanced atomic charge.
Exactly. Equal number of positive and negative charges means a neutral atom.
Question 10. If an atom contains more electrons than protons, the atom has a C negative atomic charge.
Correct. More negative charges mean a negatively charged atom overall.
Question 11. If an atom contains more protons than electrons, the atom has a B positive atomic charge.
And vice versa. More protons mean a positive charge.
Question 12. When unlike materials are in contact with each other, electrons from one material move to the surface of the other, but the protons remain on the B original surface.
Yep. Electrons are the ones that move around in this case, not the protons.
Question 13. When objects are quickly separated, both materials display a charge because one material has an excess of electrons while the other has B fewer electrons.
Right again. One gains electrons and becomes negatively charged. The other loses electrons and becomes positively charged.
Question 14. The human body in a low humidity area may have a dangerous static discharge of several B,000 volts.
It's a reminder that static electricity can pack quite a punch.
Question 15. Lightning is the C discharging of high voltage cells within clouds and from the Earth and sometimes to space.
Correct. Lightning is that massive electrostatic discharge we talked about.
Question 16. As a cloud's electrostatic charge builds up, it creates an ionized path from the cloud toward the Earth. This ionized path is called a step-down leader.
Yep, that's the path that reaches down from the cloud.
Question 17. At the same time the step leader originates, a similar ionized path called a B stepped-up streamer rises from the Earth or another positively charged object.
The upward path trying to connect with the step-down leader.
Question 18. An electrostatic discharge, lightning strike, D, equalizes the positive and negative electrostatic charges between the step-down leader and streamer.
Correct. It's the moment of connection and neutralization.
Question 19. When lightning strikes a B non-conductive object, it will produce a high temperature at the strike point, resulting in cracked concrete or the ignition of combustible materials.
That's because the non-conductive material resists the flow of the current, creating a lot of heat.
And the last one, question 20. The lightning protection system intercepts the lightning strike and provides a safe path for it to A, discharge to the Earth.
Correct. That's the whole idea behind a lightning protection system, to keep buildings and people safe.
So that was quite a deep dive. We went from the tiniest particles of the atom all the way to massive lightning strikes.
And it's all connected, you know. It's remarkable how these fundamental principles govern so much of what we see in the world around us.
So next time you get a static shock or see a lightning storm, you'll have a whole new understanding of what's going on at the atomic level.
It really makes you appreciate the power of these tiny particles and the forces at play. And who knows what other amazing connections we'll uncover as we continue to explore the world around us.
Thanks for joining us on this deep dive, everyone. Until next time.
See you then.
Bye.